Alright, welcome back everybody. When we last left our heroes, we had just found this value of pi star, the optimum portfolio balance, or weights, optimum portfolio weights, and it is a function of this gamma and this lambda. And I made a small mistake in the last video, I apologize, that lambda is actually equal to mu minus r divided by sigma. I left one of those sigmas out, and I had just defined lambda as mu minus r. So please don't make the same mistakes I do, or you're not going to be able to follow along with the slides. I've also written the definition of gamma and 1 over gamma over here, just to help us not forget what those are. To remember what the heck we're doing, we maximized pi because we had this equation here that 0 is equal to the maximum of this drift term of j for pi at all times. So what we want to do is to take this pi and now plug that back into our drift term, and that's going to give us an optimality condition. So let's do that. Plus wjw r plus, now here we're going to plug in our pi star, which is going to be minus jw over wjww times lambda over sigma. Now this is times mu minus r, and if we had another sigma, we would have lambda, right? But so lambda sigma actually equals mu minus r. So let's replace mu minus r with lambda sigma. Okay, and that's that first term. Now for the last one, we have sigma squared w squared jww. And now we have pi squared, and I'm going to distribute the square over all of these products. So we're going to get jw squared over wjww squared, w squared squared, times lambda squared over sigma squared, and that's going to be positive now because it entered as a square. Great. Okay, so now we need to do some cancellations where we can, and I need to go very, very slow on these because with all this junky algebra, it's very, very, very easy to make a mistake. So I'm actually just going to distribute this wjw term into these brackets. Feel free to watch this one on ×2, I guess. You watch them all on ×2. Do whatever you want. Alright, now over here, we can see there's a cancellation with this sigma and with this w squared and with one of the jw's. So we're going to end up with, on the top, we keep the jw squared, we keep the lambda squared. On the bottom, we cancel everything but one jww. Alright, and that's nice. Now over here we can see there's a cancellation with this sigma, so this cancels. And there's also a cancellation with this w here. I'm actually going to leave this though, because you see we have a jw here, we have a jw here, we have a jw here. What we actually want is to divide everything by wjw, because we have a jw squared here, and we have no w in the denominator of this part. So actually, if we divide everything by jw, we'll make this fraction look just like this fraction, and then we can put them together. So if we write this as jt over wjw plus r, plus that goes away, we are just left with, I guess this is minus, plus r minus jw over wjw lambda squared, everything else canceled. Now over here we said we want to make this look like this, and we did. So if we multiply this by if we divide this by wjw, we're going to cancel one of these and we're going to add a w down here. So that'll be perfect. We'll get jw over wjww. There's another w here, I apologize. Lambda squared, and there's also a 1/2. Great. So now we just need to subtract these. This is the same thing, but with a 1/2, so it's going to be minus 1/2. So our final answer will be R plus JT over WJW minus 1/2 JW over WJWW lambda squared equals 0. And this is our differential equation that gives us the optimum wealth. Given that we follow the best portfolio strategy, solving this partial differential equation will give us the optimum wealth across time. Unfortunately, we cannot solve this analytically because we have 3 differential equations, WJT, they're combined, they're not separable, it's just a big mess. So we need to make some assumptions to solve this one. And to do that, we're going to use our terminality condition, which is that JWT is equal to mu bar W, not mu bar, U bar. So if we assume a functional form, of W, or of U, so used to saying W, I can't say U anymore, that will allow us to compute derivatives, JT, JW, and JWW, then we can get an answer. But I'm going to leave that for the next video. So in the next video, we will give a form to this U of W. We'll take derivatives of it to compute what exactly are these terms JT, JW, and JWW. What it turns out is we'll actually be able to compute these terms here. We can compute this and this in terms of just a set of parameters, given that the utility function is what we define it as, and then that will allow us to then have our optimum wealth equation. So I'll see you then.